In the previous class, we looked at the interaction between nozzle flow and fan out flow, and under this category we looked at two situations. One, when a conversion nozzle is located downstream of a pipe or a duct. So, this was the situation that we looked at. So, we had a conversion nozzle which was located downstream of a pipe. So, we have flow coming in like this and going out like this. So, we had fan out flow in this section, and this is the nozzle. So, we had isentropic flow in the nozzle section. And then we also considered a situation when we had a nozzle which preceded a pipe like this, pipe or a duct like this. So, we had flow which was going through. So, we had fan out flow here, and this was the nozzle. So, we had isentropic flow in the nozzle. We looked at both these cases in the previous lecture. And today we are going to look at the interaction between flow in a convergent divergent nozzle and duct. So, the situation that we are looking at is something like this. So, we have a convergent divergent nozzle which precedes a duct or a pipe. So, we have a duct or a pipe which looks like this. So, we have flow entering this way and exiting this way. So, let us label this as section 1, this is section 2, and this is section 3, and the flow is isentropic in this part, in the nozzle part, and we have fan out flow in this part of the domain. So, if I sketch the process on a TS diagram, the diagram would look something like this. So, let us take a TS diagram, and let us say that this is my initial stagnation state. So, let us say this is T01, and let us say this is P01. So, that this is stagnation state 0, 1, and we start at let us say a subsonic state which is 1 as given here like this. So, that is the subsonic state where the Mach number is less than 1, and let us say that this is T star corresponding to this value. So, this is m equal to 1, and this is m less than 1, and this is m greater than 1. So, the flow enters at a subsonic Mach number, and then the flow reaches a supersonic Mach number at state 2. So, it undergoes an isentropic expansion process from state 1 to state 2 with the throat being at the sonic state, and after doing this we have a fan out process. So, the fan out curve for the given mass flow rate may look something like this, So, the fan out curve looks something like this. So, this is my state 2, and the fan out curve which passes through state 2 may look something like this. And if L is less than, if the length of the duct L is less than L star corresponding to Mach number M2, then state point 2 or state point 3 may lie somewhere here. So, the flow proceeds this way from 2 to 3. We have fan out flow from here to here. So, this is the fan out curve. So, this is what we get if L is less than L star. So, this is the end state for L less than L star corresponding to M2. If L is equal to L star corresponding to M2, then the exit state would lie here. So, this is when L is equal to L star corresponding to M2. Now, if the L is actually greater than L star corresponding to M2, then there is going to be a normal shock somewhere in the diversion part of the, there is going to be a normal shock in the duct somewhere, and then the flow becomes subsonic across the normal shock, and then it goes from there. So, the same situation, if I try to illustrate on this diagram, then the flow may go something like this. So, there is a normal shock and the corresponding position may be something like this. So, let us call this state x and this state as y. So, this is x and this state is y. So, the flow goes from 1 to 2 to x, and then it jumps to y, and then depending upon the exit condition it may reach state 3 or the sonic state, even if L is greater than L star. So, it will definitely reach state point 3 if L is equal to L star. If L is greater than L star, then we have a normal shock, and it may reach the sonic state even in this case, depending upon the ambient or the back pressure condition. Okay, so these are the three possible solutions. Note that in this case the mass flow rate, once we have this, because this flow is isentropic, the mass flow rate in this case is not changed as a result of the addition of the duct. Only the only thing that can change probably are the exit pressure and the presence of a shock. You may or may not have a shock depending upon the length of the duct. Unlike the previous case, the mass flow rate is not changed in this case, unless you make the shocks, unless you make this length so long that you go all the way back and change the flow in the nozzle, which is very unlikely. Okay. So, this covers all aspects of interaction between a nozzle flow and a fan flow. We can do similar thing or almost identical thing for interaction between nozzle flow and a Rayleigh flow. Okay. It is not very difficult to do. We will try to do that through a numerical example. So, the next thing that we are going to do is a numerical example. First one involving nozzle flow and a fan flow, and then another one involving nozzle flow and Rayleigh flow. We will do two examples. Let us do the first one. So, the example reads like this: air flows through a nozzle pipe combination which looks like this. So, air flows through the nozzle pipe combination shown in the figure. So, this is one, this is the throat, and this is labeled as 2. The stagnation conditions at the nozzle inlet are 1 megapascal and 500 Kelvin. The pipe diameter is 0.05 meters and it is 5 meter long. Determine the reduction in mass flow rate due to the presence of the pipe. Take F to be 0.024 and the back pressure to be 100 kilopascal. Okay. So, let us write down the information that is given in the problem. The length of the pipe is given to be 5 meters and P01 is given to be 1 megapascal, T01 is given to be 500 Kelvin. The diameter of the pipe is also given. So, area of the throat is pi times the diameter of the pipe, which is 0.05 meters. So, that is also known. Okay, so, let us leave it like this. So, that is known. So, this is the area of the throat in meter square. If I do not have the pipe, then you can see that the flow through the nozzle is definitely going to be choked, because P star corresponding to this P01 is quite high. The ambient pressure is given to be 100 kPa. So, that is given in the problem. So, P star corresponding to this P01 is going to be much higher than 100 kPa. So, in the absence of the pipe, the nozzle is definitely choked. Let us write it like this: P star can be obtained from the because the flow is isentropic, we can obtain the value from the gas tables. Let us go ahead and do that. P0 is given, and we can calculate P star like this. So, P0 over P star for this case is 1.89293. So, this is P01 divided by 1.89293, and this value comes out to be, can someone calculate this value and tell me? Five
28.3.
528 kilopascal. It is important to actually calculate the P star in these cases where the ambient pressure is given. You cannot simply assume M to be 1. You need to check to see whether M is indeed 1 or not. So, we calculate P star for this case. Since P star is greater than P ambient, which is 100 kPa, the nozzle is choked at the exit, in this case at the throat section, which means I can calculate my mass flow rate corresponding to no pipe being present. So, that corresponds to length of pipe being 0. This is nothing but P0, P01 A throat divided by square root of T01 times gamma over R times 2 over gamma plus 1 raised to the power gamma plus 1 over gamma minus 1. And if you plug in the values and take gamma to be 1.4 for this case, you get this to be 3.54 kilogram per second for the case when the pipe is absent. When the pipe is present, the stagnation pressure at the throat is known, right? That is equal to, still that is equal to P01, okay. So, first we need to see whether the flow is choked at the exit or not, okay. So, what we do is the following, if so with the pipe present, check to see if L is equal to L star. Once we do that, other things can be easily done, that is not a problem. So, we go to the Fano table, F is given to be 0.02. So, F times L over D is equal to 0.024 times 5 divided by D is 0.05, and if you evaluate this, this comes out to be 2.4, and we assume this to be L star, right? We take this to be L star. So, we say that this is L star, and we want to see whether the exit pressure P star is greater than P ambient or not. Right? So, from the Fano table, we get for this value of FL star over D, we get M throat to be approximately 0.4. And we also get P0 over P star from the table, from the Fano table. We get P over P star and also P0 over P star. So, from this we can show that P star is greater than 100 kilopascal, which is the ambient pressure, hence the nozzle is choked. Okay, is this clear? Go ahead.
P star is at exit of pipe, na?
Yeah. So P star, yeah, P star. Remember, we have assumed L to be equal to L star. So P star is at the exit of the pipe. Okay. In fact, we can, if you want, we can go through this. That is not a problem. Let us go ahead and do this calculation. Okay. So let us go to the table and get for m equal to 0.4. P0 over P can be evaluated as 1.11655 from the isentropic table. P0 is known, therefore P throat is equal to P0 is given to be 1 megapascal. So, that is 1000 kilopascal divided by 1.11655. Can someone tell me what this is? So, this is 895 kilopascal. Now, from Fano table, for m equal to 0.4, P over P star is 2.69582. So, P throat is known. So, from this I can calculate P star to be 895 kilopascal divided by 2.69582, which is 332 kilopascal. So, if I assume L to be equal to L star and then go through with this calculation, I get my P star to be 332, which is more than 100 kilopascal, which is the ambient pressure. Hence, I am safe in saying that the flow is indeed choked at the exit. If the ambient pressure is given, you must always check this to see that the pressure is more, because it cannot be less than the ambient pressure. If it is going to be subsonic at the exit, then the exit pressure has to be equal to the ambient pressure, and there is no possibility of over expansion in this case. Okay, so that you must establish if the ambient pressure is given in the problem. Okay, so this is safe, we are okay. So now the mass flow rate for a duct with of length 5 meter being present here, can be calculated like this: rho throat times U throat times A throat. So, rho UA at the throat section, and I can rewrite this as follows: rho is nothing but P over RT, and U can be written as M times square root of gamma RT, and A we leave as it is. So, this evaluated at the throat section. And if I rearrange this in terms of the stagnation quantities, I can write this as P over P0 1 times P0 1 times so the gamma square root of gamma over R comes out like this, and there is a square root of t there is a square root of t in the denominator. So, I can write this as all evaluated at the throat section. Okay. So, notice that I have multiplied and divided by a P naught 1, I have multiplied and divided by a square root of T naught 1. So, I know M throat, I know A throat, I know T01, so this can be evaluated, and I know this also, all the quantities here can be evaluated, and this mass flow rate comes out to be 2.235 kg per second. So, you can see that the mass flow rate because of the duct has reduced from 3.54 kilogram per second to a value of 2.235 kilogram per second. So, if I add a 5 meter pipe to the end of the nozzle, the mass flow rate reduces by about 37% approximately. Any questions or doubts? Okay. Let us do another example, this one involving interaction between a nozzle and a Rayleigh flow. Not exactly Rayleigh flow, but with heat addition. This problem reads like this: in an aircraft jet engine fitted with a constant area afterburner and a converging nozzle, air enters the nozzle with a stagnation temperature and pressure of 900 Kelvin and 0.5 megapascal when the afterburner is not lit, full stop. With the afterburner lit, the stagnation temperature increases to 1900 Kelvin with a 15% loss in stagnation pressure at the nozzle inlet. If the mass flow rate has to be maintained at 90 kilogram per second, determine the required nozzle area in both cases. Also determine the thrust augmentation with afterburner operation assuming that the engine is on a static test stand at sea level within bracket ambient pressure 0.1 megapascal. Assume isentropic process for the nozzle. For the fluid that passes through the afterburner, take gamma to be 4/3 and Cp to be 1.148 kilojoule per kg per Kelvin. So, this is the second worked example. Let us sketch the problem or the situation given in the problem. So, we have a constant area afterburner followed by a conversion nozzle. So, heat is when the afterburner is, so this is the afterburner, constant area afterburner, and this is the nozzle. (100 kilopascal) and P0. So, let us call this 1, let us call this 2, and this is the exit section. So, there is no problem. So, P01 is given to be 0.5 megapascal and T01 is given to be 900 Kelvin. This is without the afterburner. Okay, so, that is the first case that we are going to look at. Without afterburner, what is the mass flow rate, the throat area and the thrust that is required. M dot is given to be 90 kg per second. So, let us write this problem statement slightly differently. For both cases, gamma is given to be 4/3 and Cp is given to be 1148 joule per kg Kelvin. So, without afterburner, operation, the T0 1 is given to be 900 Kelvin. So, since the ambient pressure is given, we first need to check whether the nozzle is choked or not, right. So, when the afterburner is not operating, there is no heat addition here. So, stagnation quantities, everything remains the same. It is as if the duct is not present at all, right. So, P02 is equal to P01. So, in this case P02 is equal to P01 and P02 is equal to T01 when the afterburner is not operating. And P0 2 over P star, as you know, is equal to 2 over gamma plus 1, correct? I am sorry. Gamma plus 1 over 2 raised to the power gamma over gamma minus 1. And if I calculate this, so from this, if I calculate P star with the value of P02 that I have, I get P star to be 270 kilopascal, which is greater than the ambient pressure. That means the nozzle, the flow in the nozzle is choked and under expanded, right. So, this is flow, let me say, from the nozzle is choked at the exit and under expanded also. So, P exit is equal to 270 kPa, M exit is 1, and T02 is known. So, I can calculate T exit is equal to T star, and that is nothing but 2 over gamma plus 1 times T02 and this comes out to be 771 Kelvin. And the exit velocity UE is square root of gamma times R times TE, right, because the Mach number at exit is 1, the UE is square root of gamma R TE, and if you remember, this is gamma, Cp is nothing but gamma times R over gamma minus 1. So, we can rewrite this in terms of Cp is given in the problem. So, I can write this as gamma minus 1 over gamma times Cp times Te. So, this gives me the velocity at exit to be 543 meter per second. The nozzle is choked and the mass flow rate is given to be 90 kg per second. So, I can use the expression for choked mass flow in a nozzle, and the throat area can be calculated from our usual formula, m dot equal to P0 A throat divided by square root of T naught So, therefore, A throat when the afterburner is not in operation, if you substitute the numbers, this comes out to be 0.1359 meter square. Okay. And by using the impulse function, we can calculate the thrust. Although we have not shown this formula, we will show this later on, but for us it is easy to use it now. So, the thrust is given by the expression m dot times UE minus U infinity plus and since it is mounted on a test stand, U infinity is 0. So, this is the expression for the thrust produced by the afterburner, and if you substitute the numbers, notice that since the flow is under expanded, P minus P infinity is a positive number. So, we are going to get some thrust from both the terms. So, this comes out to be 48.87 from the first term, and from the second term we get 23.103. So, it sums up to approximately 72 kilonewtons of thrust. This is when the afterburner is not lit, that means we are not changing the stagnation temperature here. So, when the afterburner is in operation, we need to do the same calculation. So, let us see what happens when the afterburner T02 is given to be, mass flow rate has to be maintained the same, so that does not change. T02 is given to be 1900 Kelvin and P02 is given to be 0.85 times P01. It said that there is a 15% loss of stagnation pressure. So, this comes out to be 0.85 times P01, and that is nothing but 425 kilopascal. And we calculate P star once again for P01 equal to, I am sorry, for P02 equal to 425 kilopascal. P star works out to be 229 kilopascal, which is still greater than the ambient pressure. So, flow at the nozzle exit is choked and under expanded. Therefore, P exit is equal to 229 kilopascal, M exit is equal to 1, and T exit can also be calculated from the given value of the stagnation temperature. So, T exit comes out to be 1629 Kelvin, that is equal to T star, right. And velocity at the exit can be calculated in the same manner as before. So, it is square root of gamma r times T exit, and if you substitute the numbers, you get this to be 789 meter per second. So, that the thrust now with the afterburner operating, if I substitute into these two into this expression, so the thrust, the afterburner operating comes out to be 71 for the first term plus 30 for the second term, that is 101 kilo newtons. I am sorry, I am going to calculate that. Yeah, okay. So, shall we calculate that before doing this? Okay. Mass flow rate remains the same. Now, I have my quantities, so I can use this formula to calculate the new exit area. P0 is changed, T0 is changed. So, remember, or by looking at the numbers, you see that P0 has decreased from before, T0 has increased from before, M has remained the same. So, that means A throat has to increase to accommodate the same mass flow rate. So, if you calculate for these values, A throat with the afterburner in operation has to be more, and it comes out to be 0.2323 meter square. So, you can see that the area has to be, throat area has to be increased to accommodate the same mass flow rate now. If I substitute this value of the area, exit area, into my expression for thrust, which is over here. So, if I substitute, mass flow rate is the same, I have a new exit velocity, new exit pressure, ambient pressure is the same, I have new exit area. If I substitute these values into this, then I get thrust with the afterburner in operation to be 71 plus 30, that is 101 kilonewton, which is roughly a 40% increase in the thrust. So, this shows that the afterburner is an extremely useful and convenient device for short term thrust augmentation. It is very simple in construction, and if you want short term thrust augment, it is not very efficient, but if you want short term thrust augmentation, then it is a very effective way of achieving that. You get a 40% increase by injecting more fuel into the stream here, burning it, increasing the stagnation temperature, and then expanding it in the nozzle with increased area. So, the only additional complexity is that the area of the nozzle has to be increased. So, which means you need a variable area, variable throat area nozzle when an afterburner is connected to the engine, and we will see how these nozzles are fabricated later on when we talk about afterburning engines. Okay. But this demonstrates the augmentation in thrust that is possible. Okay. Now, one point that we discussed earlier has to do with P0 over P ambient. Now, if you take the case without afterburner operation, you can see that P0 is 500 megapascal. So, P0 over P ambient is 5, correct. The question is, since P0 over P ambient is 5 and I am using only a convergent nozzle, if I had used a convergent divergent nozzle, how much would the thrust have increased? Would I have gotten a lot more extra thrust, or is it about the same, not worth doing a convergent divergent nozzle? We will examine that next just to complete the problem. Okay. So, we are looking at a situation when the afterburner is not operating. So, that is a simple thing to look at, and we are going to use a convergent divergent nozzle, right. So, since P0 over P ambient is equal to 5, in this case 500 kilopascal over 100 kilopascal, it is 5. Is it better or beneficial to use earlier we stated that if P0 by P ambient is more than 3 or 4 approximately, it may be better to use a convergent divergent nozzle. Let us see whether that is true or not. So, if you are going to use a CD nozzle and we expand the fluid correctly to the ambient pressure, right. So, at the exit of the CD nozzle, the flow is correctly expanded and so P is equal to P ambient is equal to 100 kilopascal. So, this means P0 over PE is equal to 5, and we also know that since the flow is isentropic, this is nothing but 1 plus gamma minus 1 over 2 times ME square raised to the power gamma over gamma minus 1. So, I substitute gamma equal to 4/3 and I can solve this equation to obtain ME, right. To solve, to get ME to be 1.73. In fact, if I had expanded the flow all the way to atmospheric pressure, my exit Mach number would be supersonic and correctly expanded. So, once I have ME, I can get my exit temperature, static temperature. I know the stagnation temperature, so I can get my exit static temperature from T0 1 divided by 1 plus gamma minus 1 over 2 times ME square, and this gives me 602 Kelvin. And using these two values, exit Mach number and static temperature, I can get my U exit as ME times square root of gamma RTE, and the exit velocity comes out to be 830 meter per second. So the exit velocity with the conversion nozzle came out to be 543 meter per second. Now the exit velocity with the conversion diversion nozzle comes out to be 830 meter per second. But PE is equal to P ambient, which is also P infinity. So if you now evaluate the thrust that the nozzle is going to develop, notice that if you look at these two terms, now with the conversion diversion nozzle, this is going to be 0 because PE is equal to P ambient, only this contributes to the thrust. So thrust in this case is going to be, so if you substitute the numbers, you get the thrust to be about 75 kilonewtons. Earlier it was 72 kilonewtons, now it is about 75 kilonewtons, and improvement of 3 kilonewtons. So definitely there is an improvement, and the improvement will become better as your P0 over P ambient keeps increasing. It is 5 in this case. As it keeps getting better, it will become more and more. So this shows that for these kinds of ratios, P0 over P ambient, it may not be worth having a conversion diversion nozzle because of the normal shock during startup and the complexity that it brings in. So it may be, we may be better off just using a conversion nozzle in this case. Okay, any questions? Okay, so that concludes our chapter on quasi one dimensional flows. We will start the next chapter on oblique shock waves.